This is an introduction to Boolean algebra and digital logic design. Boolean algebra and digital logic design principles are the basis for the development of computing circuitry. Logic, as we know it, is captured in a formal system, the Boolean algebra, and then used to map logic functions on hardware, actual circuits, which implement computers. So what we're going to do in this introduction is we're going to go over Boolean algebra, the basics of Boolean algebra, and then we're going to show how electronic circuits actually implement the operators of Boolean algebra, and therefore how Boolean functions, logic functions, can be implemented using digital circuitry. And then we're going to talk about certain components that later we will see how they're used in order to build computer hardware. Boolean algebra, to begin with, is what its name says. It's an algebra, it's a formal system which attempts to capture logic in a mathematical formulation. So it is all about encoding logic and logic operations. Entities called logic variables take on logic values. That is what makes this whole thing an algebra, that you have variables which take on values, except that unlike the normal algebra that we all know of, the values that these variables take now are just two logic values, the true and the false. A logic variable can only assume one of these two values, nothing else. Consequently, if it is known that the value of a logic variable is not true, then it must be false. And conversely, if it's known that it is not false, then it must be true. A logic variable can represent the state of validity of any statement which will either be true or false. For example, the Boolean logic variable x may represent the validity of the statement "it is sunny now," or "the temperature exceeds 80 degrees," or "the pressure exceeds 30 millibars," etc. Now, each one of these statements evaluates to one of two possibilities. It's either true or it's false. Now, if you use a symbol like x, a variable, to represent the state of validity of a statement like this, then that variable is a logic variable or Boolean logic variable. Suppose that x represents the validity of the statement "the temperature exceeds 80 degrees." Now suppose that another variable y represents the validity of the statement "the temperature does not exceed 80 degrees." As the temperature varies, the variables x and y will always have opposite values. When x assumes the value of true, y assumes the value of false, and vice versa. These are called complementary, or we say that one is the complement of the other, sort of one being the opposite of the other. Now, we need a notation in order to represent the fact that one variable is the complement of another. And we represent this fact by this notation here. X equals y cap, or y and then followed by a quote. The quote complements, i.e. flips, inverts, negates, or toggles the value of the variable on which it is applied. Therefore, the quote is an operator which operates on an operand. This operand will be a variable or a combination of variables, as we're going to see later. And what it does is it transforms this variable in the specific way of inverting its prior value. So if x is true, then x complement will be false. Boolean operators. Just like the negation operator that we saw earlier, that we signified with a quote, there are two more basic operators which make the algebra work. Those are the AND and the NOT operators. The AND operator, which we also denote as a dot, operates on two arguments as follows: x and y. The outcome is true if both the x and y variables have values of true. If any one of the two has a value of false, then the outcome of the operation is false. This definition is usually given in a formal tabular form, which defines the outcome of the operation exhaustively for all possible cases or combinations of operand values. So in this table, you see the inputs x and y, and here you have all the possible combinations for their values. And then on this column, you have the outcome of the x and y combined with the operator AND. So the AND operation on x and y. And as you see, when both inputs are false, the outcome is false. If any one is false, the outcome is false. And if both the inputs are true, then the outcome is true. That is the formalization of our intuitive understanding of the operand AND, or the logic combination signified by the AND. For simplicity of notation, instead of writing false and true all the time, we adopt an encoding of the true and false values by using the symbols 1 and 0 respectively. So for the purposes of Boolean algebra, 1 and 0 are representing the only two possible values, and they're just that. They just represent the two possible values, true and false. The previous table that we had over here is now transformed by this encoding to this table over here. There is one interesting observation to make here. Note that the first two rows of this table, where the y variable is false, the output is false. On the next two rows, where the y is 1, the output is whatever x is. So we can summarize these two lines in the following statement. Any variable that is logically ANDed with a logic 0 yields a logic 0. Similarly, for these two lines, we see that any variable x that is logically ANDed with a logic 1 simply produces exactly the same value as the variable x. So in other words, if y is 1, then x simply passes to the output. Now this is reminiscent to the way multiplication works with the constants of 0 and 1 in the classic algebra. And it's perhaps because of this that the AND operator is also denoted as a dot, as a shorthand notation, much like the way multiplication is denoted in classic algebra. The OR operator, which is also denoted as a plus. The OR operator operates on two arguments as follows. X or y, the outcome is true if any of the x or y variables has a value of true. If both of them have false values, then the outcome is going to be false. This definition is usually given in a formal tabular form like this. So wherever you have both variables of the input being false, the combination is going to be false. In any other case where you have at least one of the inputs being 1, the outcome is 1 or true. And this table again can be summarized in this form by using the encoding of 0 and 1 for the values false and true. Looking at the first two rows where the y variable is 0, the outcome is exactly what x is. So we can summarize these two lines with a statement that any variable ORed with a false value passes that variable's value unchanged as the result. The next two lines where y is 1 and the outcome is 1 is summarized as follows. Any variable ORed, logically ORed, with a logic 1 or a true value yields a true outcome. This is reminiscent to the way addition works with the constants of 0 and 1 in the classic algebra. And perhaps it is because of that that the OR operator is also denoted as a plus symbol in a shorthand notation. But notice that in Boolean algebra, 1 plus 1 is 1, as in true, or as in true is true. Whereas in classic algebra, this would be 1 plus 1 is 2. Remember, however, while we're using the same symbols, zeros and ones, that are used in classic algebra, this is not classic algebra. This is Boolean algebra, and there are only two values, 0 and 1. So no operation can assume any value outside 0 and 1. Therefore, in Boolean algebra, 1 plus 1 is 1. And that is because of this line of this table. Boolean expressions. Now, using the logic variables and the operators of AND, OR, and complementation that we saw earlier, we can now build composite expressions. For example, consider the following variables. X is the value of the statement the temperature exceeds 80 degrees. So you evaluate this statement to either a true or false, and that's the value of x. Similarly, you have other variables, y, z, and p, being different statements that evaluate to either true or false, as shown here. Each of these statements is either true or false at any given time, and that is the logic value of the corresponding logic variable. Now consider how composite expressions can be built out of combining these variables using the Boolean operators. Say, for example, that C is X and Y. C represents the validity of the composite statement, the temperature exceeds 80 degrees and the pressure exceeds 30 millibars. The composite statement is true, in other words, the whole thing as a composite statement is true if both the involved statements are true. If either of them is not true, then the composite is not true either. Again, consider another expression that's more complicated now. So here you have x and z, or the complement of x and complement of z, and then this composite is ANDed together with another composite statement that is included in the orange brackets and which consists of a logical OR of this statement, which is made out of y and p, and this statement, which is made out of the negation of y and the negation of p. This expression represents the validity of the composite statement that you can see over here. And in this example, the brackets and the colors of the brackets are maintained so that you can follow which part of this whole composite statement that starts from here and ends here correspond to which parts. So for example, this one, the red part that you see over here, corresponds to this expression, which is in red font. The temperature exceeds 80 degrees and the heating element must be shut down. Or, this is the operator OR, and then the expression that is in purple is shown over here. Okay, and then this composite statement in the green brackets is logically combined through an AND logic operation with this composite statement that starts here and ends here and is included in the orange brackets. That represents this whole part. Anyway, my point here is that using these logic operators of AND, OR, and NOT, you can build very complex, arbitrarily complex statements which we call Boolean expressions out of combining simpler statements or variables. Now looking at this expression, since it is a logical AND of this sub-expression in the green brackets and this sub-expression in the orange brackets, in order for the whole thing to be true, to evaluate to true, then both this sub-expression and this sub-expression have to evaluate to true at the same time. In turn, in order for this part to be true, either this term, this sub-expression, or this sub-expression, or both, must be true. And then you can go on like that, analyzing what the possibilities would be. But again, the point here is that you can build complex Boolean expressions out of simpler ones by combining them with the Boolean operators of AND, OR, and NOT. Two different expressions, say E1 and E2, are called equivalent, or they're considered to be the same, if they are indistinguishable, which means that their validities are always the same. Okay? They evaluate to the same value always. In other words, they both produce the same logic value always for any combination of values for the logic variables that they may involve. We signify this by the equality between the two expressions. As we're going to see, the expression x and y and then the complementation of the whole thing is actually the same as taking the complement of x and then taking the complement of y and then ORing them together. If you look closely here, you will see that these two expressions are different. Okay, they appear to be different. However, if you exhaustively run down their truth tables, which means all the possibilities, take all the possibilities of inputs. If you take all the possibilities if you take all the possible combinations of inputs and you look into what value each of these expressions produces, you will find that they're exactly the same. This is called the truth table for these expressions. Let's look over this table a little bit more carefully. We have the two variables, and then here we have an exhaustive listing of all the possible combinations of values that they may assume. If you have two variables, you have four possible such combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Now, looking at the combination of x and y, using the same truth table that we saw earlier for the AND operator, we get this column. It will be 1 only in the case where both inputs are 1s, and 0 everywhere else. Now take the complement of this, that is this expression. So in this column, we're going to take this one and complement the values to obtain these. So all the zeros become 1s, and the 1s become 0s. Now, looking into this expression, for these input combinations, the complement values are going to be these, and the outcome of this operation is going to be this. So you're going to have 1 or 1, and according to the truth table for the Boolean operator OR, 1 or 1 evaluates to 1. 1 or 0 evaluates to 1, and 0 or 0 evaluates to 0. So after we exhaustively run all the possible input combinations, and we compute the values that each one of the expressions generate, we find out that they have the exact same output. You look at this column, it's identical to this column. Therefore, we say that these two expressions are indistinguishable under any possible input combination. Therefore, we call them equivalent or the same, and we write this expression to indicate that. Incidentally, this identity is known as the De Morgan's law. We're going to see a lot more of that later, but remember this name, De Morgan's law. In a similar way, using truth tables again, we can prove the dual of the previous. The previous was x and y complement is the OR of the complements. Over here we have the complement of the OR is the logical AND of the complements. This is also known as De Morgan's law. It's actually one of two dual statements that are known as De Morgan's law. So if you would like to look over how this is done, you can check this truth table over here, where we have all the possible input combinations and then the computations for its expression, yielding this column for the first expression and this column for the second expression. And we see that the two columns are the same. Therefore, these expressions are indistinguishable under any input combination because they yield the exact same results. Therefore, they are the same. Further, we can prove a whole bunch of other identities, which means expressions that are always true, that are given in a tabular form here. And of course, they can be obtained by any reference on Boolean algebra. I'm not going to go and read over them one by one, but I encourage you to just look carefully over them and realize that these operators of AND and OR, they obey the commutative law, the associative law, and you can see over here that you can use the distributive law, which means you can distribute a value inside a parenthesis in this way or in this way. So one other thing to note is that we have dropped the use of the dot for simplicity. Just like in standard algebra, we indicate often multiplication by just putting variables one next to the other without the dot in between. We can do that here too. It's all a matter of just notation and simplicity of notation. So dropping the dot simply makes the logical end be indicated by the sequence of two variables put together. And of course, we do still maintain the plus symbol for the OR operation. Now, armed with the knowledge of the basic Boolean laws, we can manipulate Boolean expressions and alter their form without changing their validity. For example, take this expression. Using the distributive law, which is this line right here of identities that we can prove in the same way that we did over here. So now using the distributive law, and particularly this, we can see that this is the same as this. Now, this, using the inverse law, is evaluating to 1, and then x and 1, using the identity law, evaluates to x. Therefore, we have proven that this is the same as this. Hence, we have transformed the original expression that we had, which looked a little bit complicated, to a trivial expression, which is just x, by using transformations which preserve the logic value of the original expression, and then shown that it can be reduced to this. Now, this same thing can also be shown using truth tables. So we can get a truth table and plot this expression and then plot this one. Now, you might ask, but this one is just one variable. Okay, so if you have a truth table like this, you have combinations for variables x and y, but then over here you can have just one variable, which will be simply what its relationship is with the input variables. So that's no problem that this one is just one variable and this is two. But you will see that under the column for this expression, you're going to have combinations that are exactly the same as this one. So we can show this by truth tables, but this is an alternative way to prove an equivalence by doing direct Boolean algebraic manipulations of the expressions. Let me give you another example. Let's take this expression here, x and y naught, or y. So here are some mathematical acrobatics that we can do that are based on the identities that we saw over here. So for one thing, the y is replaced by y and logic 1, because y and logic 1 leaves y unchanged. But then the logic 1 also comes from getting a variable x and ORing it with its complement. And then using the distributive law, we can distribute the y in here and get these terms. Now, we can duplicate this term. We can duplicate this term here, as you see over here, because it changes nothing. It's like x or x is still x. So this term, or itself, it's still just itself, just this. And so this one here now is the same as this. All we did over here was to simply transpose the two variables. It has changed nothing. And then taking the two first terms and factoring out the x, according to the distributive law, we get this term. And similarly, factoring out the y from these two terms gives us this. Now this one is evaluating to 1 because it's a variable or its complement, and similarly for this one it's a 1, therefore we get what? We get x or y. Hence we have proven by direct algebraic manipulation that this expression is the same as this. Again, we could have done this with truth tables just as well, but I wanted to show you here the alternative way of doing direct algebraic manipulations to transform the expressions. We started with this expression and equivalently transformed it in different forms that are guaranteed to not change its value until we arrived at this one. And in the process of doing that, we used these identities that have been proven. You can prove them by basic truth tables. They have been proven to always hold true, and therefore they become identities or theorems, if you like, that you can use in this algebra. Let's revisit the previous example of this composite statement. The expression can be restated like this. So what I did here was that I performed a few manipulations in order to show that the whole expression can actually be expressed like this. Let's see how. If you take this, then this is the same as this. This comes from taking each one of these terms and multiplying it with this term, or logically ending it with this term. So this is obtained by distributing this term into the terms of this parenthesis. So you have the xz part and this, that's this term, and then you have the x naught, z naught with this term, that's this. Further, you can distribute this term into the terms of this parenthesis and this term into the terms of this parenthesis and obtain all this thing. This provides two alternative but equivalent forms for the original expression. The original expression was this. This is the same as this. If you drop the dots and you retain the complements and the or signs, that's what you get. But then we saw that this is the same as this. So these are equivalent. Now, this form is called the product of sums form. The product is signifying the logical end. Remember that the logical end kind of resembles the product of the standard algebra. So when people were looking for a name for this form, they called it the product of sums. Whereas this one here is the sums of product terms. So this one is known as the POS form, and this is known as the SOP form. They're both representations of equivalent expressions, but they're known as standard or standardized forms for regular expressions. This is why they're called standardized. Consider this expression. You see, this expression is the same as this expression, which is the same as this expression. So all of these three forms, they're basically forms of the same expression, equivalent expressions. So if an expression can have different forms, sometimes we want to standardize the form that it is in for various reasons. We want to have a way to describe an expression in a standardized form. And either the SOP or the POS forms are the two standardized forms that we usually find expressions in or refer to. Considering the SOP form, this one, it is clear that for the whole expression to be true, at least one of the terms in this SOP form must be true. Any chosen term tells the story of how the expression may be made true. So in other words, each one of these terms represents a scenario for making this whole composite statement true. For example, the term x, z, y naught, and p naught represents the scenario: the temperature is excessive and the heating must be shut off, and the pressure is not excessive, and the pressure release valve need not be opened. So this would be one scenario for this whole expression, composite expression, to be true. And all of these terms indicate the collection of all the scenarios exhaustively that would make this statement true. So let's review what it is that we can do with Boolean algebra. We can capture logic structures in formal statements of algebraic form, that is, the expressions that we saw. We can manipulate these logic structures and transform them to equivalent ones of different forms. Similarly, we can simplify an expression to an equivalent but simpler form. This may reveal a simpler representation or understanding of the corresponding logic structure represented by the expression. And we can prove or disprove that two expressions are of the same value, or that are of the same validity, as we say. So now you ask, so then what? What with all this? Well, we are on a path to figure out a physical mechanism which will be able to perform the operations of Boolean algebra and consequently perform functions that can be represented as Boolean expressions. Even better, we would like to come up with a computing mechanism, which we can then feed a logic expression representing a desired function and have it perform the function described by the expression. So it sounds like we're after a computer that we can program to do a job. Think about it. If we're looking for a mechanism to which we can feed a logic expression that specifies a desired logic function and have it perform that function, then what is it that we're asking? We're asking to make a computer that we can program to do a particular logic job. Now, in order to get a start, we would need a physical mechanism that can simulate the basic operators and thus perform the simple logical functions and, or, and not. And guess what? We do have them. And before I explain how they are built, let me talk a little bit about transistors. I don't want to turn this into an electronics lecture, but it is important to understand one particular property of the famous transistor. This is how a transistor is depicted in circuitry schematics, in circuits, in other words. Over here, I have an equivalent representation for the transistor, showing it practically as a switch. So there is this contact over here that is either open or closed. So it allows, say, current to flow from this line to this line. If the switch is closed, then current will flow. So this switch will be closed and these two leads will be practically shorted. And if the switch is open, then the signal path from this line to this line is cut, and the voltages of these two lines may be different. Now, this is just what a simple switch will do, but in the case of the transistor, what happens is you have a third input, which is called the base, and applying a voltage on this base basically controls this switch. So for all practical purposes, actually for all practical digital logic purposes, a transistor can be viewed as an electronically controlled switch. That it is a switch that's electronically controlled by the state of this input. So if this input is 0, then this is an open switch, and if the input here is a 1, then this is a closed switch, and these two leads are shorted. Here we're going to see how the operation of inversion, the logical NOT, can be implemented by an actual electronic circuit. First, we have to understand that when it comes to circuits, you have voltages and currents. The logic values, the logic 1 and the logic 0, are represented in the circuits by voltages. And it is generally the case that 5 volts is chosen to be the reference voltage for the value of true or logic 1, and 0 volts or ground represent the reference voltage for the value 0 or false. In this figure, we have a transistor that is connected with two resistors to an input and a power source, shown as VCC. On the other hand, over here, it is grounded to the ground. And the output of the circuit taps this end of the transistor. Now, let's try to understand how this works. In order to understand this, let's use the previous conceptual equivalent and replace this transistor with its corresponding logic-controlled switch or electronically controlled switch. If the voltage over here that is appearing as input is a 0, then this switch is open. With this switch being open, there is no current flowing this way. All of the current is flowing this way. And assuming that whatever you connect over here doesn't draw too much current, the voltage that you see over here will be that of the power source, minus any drop of voltage on this resistor, and that is why I said earlier that it is assumed that you're not drawing too much current, so the voltage drop across this resistor is negligible. So what you see at the output over here is in fact VCC. And if this VCC, the supply voltage is 5 volts, then at the output you see a logic 1, because 5 volts is the representation of the logic 1 value. If on the other hand, this input is a logic 1, which means that it is 5 volts, then what happens is this switch over here is closed. With this switch closed, this point here is shorted to the ground. So what do you measure at the output? You will measure 0 volts, which is the logic 0. Incidentally, the reason for this resistor over here is that when this switch is closed, it prevents this power supply from being shorted to the ground directly. So if the input is 5 volts, over here you get 0 volts, So if the input is logic 1, the output is logic 0. And as we saw earlier, if this is logic 0, this is going to be logic 1. Therefore, this circuit behaves exactly as an inverter if the logic values of 0 and 1 are represented by corresponding ground and 5-volt reference voltage levels. For the purposes of circuits, we represent this as this shorthand notation. This is an inverter. Now this is not required material, but I thought that it would be nice for you to understand how all this Boolean algebra abstracts turns into actual physical circuitry that implement the operators. And we come to the implementation of the logic OR. In this circuit, we have two diodes. These are the symbols for electronic diodes. What diodes do is that they allow current to only pass in one direction through them. So they will allow current to pass in this direction, but they will not allow current to pass in the other direction. So if there is any voltage over here, that voltage will cause current to flow to the ground in this way. Similarly for Y. Otherwise, current will not be able to go back this way. So if this was a negative voltage, okay, it should cause current to flow, say, from a positive voltage over here to flow this way back to the negative voltage, but this will prevent that from happening because while this one will allow current to go this way, this will not allow current to go this way. All right, so let's see how this works. If both of these are zeros, then there is nothing pushing any current out here, and therefore what you will measure at this output will be the ground. There will be no current here, therefore no voltage drop across this resistor. Therefore, the voltage at this node will be exactly the same as the ground. So this will be a logic 0 if both of x and y are zeros. However, if any of the two is 5 volts, then the corresponding diode is going to let current through to feed the output. This resistor will prevent the voltage of this line to be shorted to the ground. Of course, there will be current flowing through here that will cause a voltage drop so that this will be maintained at above the ground voltage. Bottom line, if any of the two is 5 volts, you're going to measure 5 volts at the output, or almost 5 volts. The drop across these devices is negligible, so you will see 5 volts if any of the two is 5 volts. So that implements the logical OR. The logical OR is specified in logic circuits like this, in this way, and this is the physical implementation of it. Next, a circuit for the logical AND. Here we have two transistors and of course two inputs connected in this way. Now this is basically like having two switches connected in cascade. So this is the output right here, and the voltage will flow to the output if both these switches are closed. So if X and Y are both 5 volts, logic ones that is, then these electronically controlled switches will be closed and this voltage will flow through this connection to the output. So you're going to see 5 volts at the output, which is a logic 1. and this resistor prevents then this power source to be shorted to the ground. If any of X or Y is 0 volts, representing a logic 0, then the corresponding switch will be open. Any of the two being open means that the circuitry from VCC to the output is open, and therefore there will be nothing feeding this output. There will be no voltage drop across this resistor. Therefore, the voltage of this line will be tied to the ground, so what you will have is a logic 0. That implements exactly the logic AND operation. And we specify this with this symbol for the purposes of logic circuit and logic circuitry. There are some other circuits that implement some alternative gates that we call universal. They're very important because of the properties that they have. These are the NOR and the NAND. The NOR is a regular OR. It's a regular OR which is followed by an inverter. This circle over here means that this function here is in fact inverter. So this is like the OR followed by an inverter. And this shorthand, the OR with the circle on its output, is the symbol that we use to signify the NOR circuit to digital circuits. And similarly, we have the Nand Gate, which is an AND followed by a NOT, and similarly is designated in this way with a little circle at the output of the AND gate. There is something interesting to note here. If you provide the same signal to both inputs of either the NOR or the NAND, then the output is going to be the same input signal inverted. It's easy to see that because if you consider what this does, it takes the logical OR of these two signals, which are both X. So logical OR of the two inputs, which is X, followed by a NOT. Now, X or X is X, according to the earlier identities that we saw. And so this will be the X inverted. Therefore, doing this trick provides an inverter for X. Now, if you cascade a NOR gate with this same structure, which, as we said, works as an inverter, then what are we going to have is we're going to have an OR gate, because this inverter will basically invert the previous inversion. So an inversion of an inversion leaves things as they are. So basically this will cancel that inversion, and this will then behave just like a regular OR gate. Finally, if we invert the two inputs of a NOR gate, we're going to effectively produce a AND gate, an AND logic mechanism. Let's take a look at how this works. So if its input is inverted, so this is X naught or Y naught, and then the naught of the NOR inverts the whole thing, then by De Morgan's law, this is the same as XY. Therefore, this mechanism effectively is a logical AND mechanism. So in conclusion, we see that we can make all of the basic fundamental gates, the AND, OR, and NOT, which as we saw make up all possible expressions in Boolean algebra. We can make them out of NOR gates alone. So if you were in a lab and you didn't have anything but only NOR gates, you could still build any logic circuit that you could specify in a Boolean expression. And that is because you can use this trick to make inverters, you can use this trick to make OR gates, and you can use this trick to make AND gates. Similarly, you have the Nand gates, which are also universal, and you can similarly make a NOT gate out of them by shorting its inputs. It's clearly shown in this algebraic form over here. And you can cascade a NAND gate with an inverter to cancel the inversion of the original NAND gate and therefore make a regular AND gate. And similarly, if you invert both inputs of a NAND gate, according to De Morgan's law, inverting both inputs and then inverting the logical end of this yields X or Y, which means that this effectively is a mechanism that implements a logic OR. Therefore, the NAND gates are also universal because out of NAND gates alone, you can make just about any circuit implemented with AND, OR, and NOT operators of the Boolean algebra. Now, there are certain algorithms that allow you to transform an expression given in any standard form, like a SOP form, sum of products form, into a form that involves only NAND or only NOR operations. But that goes beyond the scope of what we need to do in this course, so I'm skipping that. Another gate that is interesting to know is the XOR gate, or the exclusive OR gate. It is like the regular OR gate, except that it is 0 when both of the inputs are ones. So in essence, the XOR gate, or the XOR function, if you wish, simply yields a 1 when both inputs are different, and it yields a 0 when the both inputs are the same, either both zeros or both ones. Now, you can make this out of AND and OR and NOT gates like this. This circuit, you can verify that it is doing exactly what is specified in this truth table. And so this is how an XOR gate is made, and this is the symbol that we use to depict this one in logic circuits. So now what? What can we do with all this stuff? Well, we can use these basic circuitry parts as the building blocks for constructing circuits that perform logic functions from simple to very complex. We will progress to explaining the circuitry that is used to build computers. That is part of the architecture of a computer and the ways such architectures have evolved. We will start with showing basic structures that allow data to be stored, transported, and manipulated. These operations, in turn, will help illustrate how a basic computer works, how it manipulates data, and how it executes a program. Then we will proceed to explain the advances made in processing data in high-throughput systems. What we will need is some intuition into the way that these circuits operate, and I'd like to develop this intuitive understanding of their operation rather than just sticking to the mathematical operations. So let's say you have a AND gate and two inputs to it, X and Y, and this is what the truth table of the AND gate is. If you were to observe the output over time, then this is one way to explain the output. This is the signal X. The horizontal axis in these waveforms represents time. So this waveform over here shows the values of X over time, and the values are either zeros or ones. So for certain periods of time, the value of X is zeros, and some other periods of time, the value of X is ones. Similarly, this shows the waveform for the other input, the Y, and shown that, again, it is 1 or 0 in different time intervals. So if we are to look at the output waveform and see what the output is going to be, notice that according to this table, whenever Y is 0, the output is 0. And whenever the Y is 1, then the output is exactly what the input X is. So when Y is 0, the output is going to be 0. Okay, so looking at these two waveforms, this spot and this spot where the Y's are zeros, the output will be zeros. In the green bands, which is where the Y is 1, the output will be whatever the input is. So in the green bands, that's when Y opens the door for the input signal to pass as is at the output. So the bottom line is that the AND gate acts as a switch that lets one input, the X in this case, pass to its output based on whether the other input is active or not. This works similarly if you have more than two signals, say AND signals, which are all ANDed together. If the first n minus 1 signals are true, then the output is whatever the nth signal is. This view will be important to intuitively understand the functionality of certain circuits in the following. Here is one logical circuit that is made out of the gates that we just talked about. This one is called a demultiplexer. It has three inputs. One is this one, the X, and then there is another two inputs over here signified as A and B. We call these control inputs, and it's going to become apparent in a moment why they're called control inputs. There are four outputs over here, and let's see how this circuit operates. When these inputs are both zeros, then the two red lines are ones only, and the blue lines are going to be carrying the zeros. So if you notice this gate right here, two of its inputs come from the red line, so they're both ones. According to the view that we presented a little earlier about the AND gate acting as a gateway for a signal to pass to its output depending on the other control signals, this signal X will pass on the output of this AND gate because its other inputs are ones, but any of the other gates will have at least one zero input because they feed off of some of the blue lines. So this one here will have both of these inputs being zeros. This here is going to have this input being 0. This one is going to have this input being 0. And so all of these gates will block the passage of the signal X to the output. Their outputs are going to be zeros. So this is why these two inputs are called control inputs. They're also sometimes referred to as address input. And that is because they provide an indication or an index for the gate that will be activated to allow the input X to pass on the output. So a 1 and 1 will feed logic 1s to the blue lines. So this gate here is going to have two of its inputs being 1s. So the X signal will pass to the output and will appear over here. The other gates now, because at least one of their inputs is fed by the red lines, which are carrying zeros, there will be blocking the signal X, and their outputs are going to be zeros. So this one here is called a demultiplexer because it demultiplexes the X signal to one of these lines depending on what the control or address signal inputs are. So if both of these are zeros, the signal is going to appear over here. If they are 0 and 1, it will appear here. 1 and 0, it will appear over here. And 1, 1, it will appear over here. So this is a very useful circuit, and in fact, you can find it on the market on chips that are called demultiplexers. And the important part of this, other than just serving as an example of what you can do with gates, is that this is a way to control electronically using the control signals A and B where the signal X will be directed and so to which output it will appear. Again, this is an electronically controlled gateway because depending on the electronic values of the signals A and B, you determine where the signal X will be directed. As we're going to see a little bit later, this is one part of making data paths that are adjustable electronically under the control of control signals, and therefore establishing how data will be transported from where to where can be electronically controlled. This will be important when we talk about the internals of a computer and how it's made. Here is a circuit that does the exact opposite, and it's called a multiplexer. This one has these inputs. It still has these two control lines, again inputs, but it has a single output. And these control signals select one of the inputs to pass to the output. So when these signals have values of 0 and 0, then the red lines are 1s. This gate is the only one that receives both 1s on these lines, and so it will allow the signal X0 to pass at its output. The rest of the gates will tap at least one of the blue lines, so they will have at least one input that is 0. Therefore, they will block anything else, and their outputs are going to be zeros. So the OR gate over here, collecting all of these lines, any line that happens to be a 1 will pass on the output. So if both A and B are zeros, and this is a 0, then this is going to pass at the output of this gate. All of these gates will have zeros. The OR will see zeros everywhere. The output will be 0, exactly like this one. If this one is a 1, then this gate will allow that to pass to its output. The OR gate will see a 1 now at one of its inputs. It will allow it to pass out, and so what we will get over here will be the value exactly like X0. So in both cases, the output will be exactly what X0 is if A and B are both zeros. If A and B are 1s, then this gate, tapping the blue lines that carry the 1 logic values, will allow its input X3 to pass to the output, and therefore through the OR gate to pass to the final output here. And if you have different combinations, then all of these signals will be selected according to this table here. So again, this is another example where data paths are established dynamically under the control of input logic signals. And depending on what these signals are, the corresponding input will be selected to pass to the output. Let's put these two together. We have over here a multiplexer, and the output for the multiplexer is sent to the input of a demultiplexer. We have 4 inputs here, we have 4 outputs here, and of course we have the control signals for these two blocks of logic circuits. Now, depending on what you choose for AB and for CD, one input will be selected to pass to this line, and then this, depending on what the CD is, will be selected to pass to one of these outputs. That way, with an input combination with an appropriate input combination for A and B, you can select any of these inputs to pass to this line, and then with another combination of C and D, you can select to which output this signal is going to appear. So you can have any one of these effectively connected to any one of these outputs based on what you choose A, B, and CD to be. Thus, this is a way to control electronically which input is going to be directed to which output. And this provides an example of how data can be transferred or routed among the various internal components of a computer. This is a very simple example that shows the routing of a 1 bit of data. But imagine that you can stack this apparatus into a bunch of different layers, each one of which is carrying 1 bit. So in a layered scheme, you can carry a whole input vector to an output vector, or to a vector of outputs. And of course, the signals, the control signals A, B, and CD, they can be the same, they can be fed the same to all the layers of this structure. So you may have, for example, where you have x0, you may have x01, x02, x03, and so on. You may have a whole number of bits, say 16 bits, in a layered structure where you have 16 layers. And the A, B signals are fed to all the layers. So you select the whole vector that is stacked over here in the place of x0, and then you can direct it in the same way to the output stack that sits on one of these y's over here, if you assume that all of these layers again are being fed the same control signals C and D. Bottom line, this is a way to create dynamically controlled signal paths based on control signals alone, without any mechanical switching, that is. While we're at it, let's talk about decoders. This is another very useful logic circuitry that is also found on chips that are sold specifically as decoders. So decoders will take n inputs, and they have 2 to the n, 2 to the power of n outputs. So if this was 2 inputs here, you would have 2 to the 2 outputs, 4 outputs here. If you had 3 inputs, the outputs would be 8, or 2 to the 3. 4 would be 16, and so on. So the way the decoder works is that you provide an input combination over here. And then one out of these 2 to the n outputs will light up. It will be activated. Only one of these 2 to the n outputs will be activated. The rest of them will be at logic 0. So you can view these outputs as detectors, which detect which particular combination of values has been fed at the input. That is why these outputs have to be 2 to the n, because if you have n binary inputs, the possible combinations of values that you may have are 2 to the n. Among other things, they are useful in selecting one out of many registers to activate, or a memory location out of a memory system according to binary control values that are placed on the address lines of a memory bus. So we will see later that the bunch of signals that transfer data, they're referred to as buses. And if a decoder like this is connected to a bus and is able to view the data that is dropped on the bus, then the outputs over here will basically detect which particular combination has appeared at the input, and therefore which particular combination of values is actually being transferred on the bus. This is what a decoder looks like. This is a decoder that has 2 inputs and 4 outputs. As you see, what it consists of is AND gates, which basically are wired to detect every possible combination of input values. So as you see, every signal, every input signal over here is also inverted. So you have the signal and the inversion, and each gate taps either the original signal or the inverted signal of one of the inputs. So this one over here taps the uninverted inputs. So this one here taps the original signals X and Y. And this one here taps the signals X and Y naught. This one taps the signals X naught and Y. And this one taps the inversions of both. This one is a boo-boo. It should be XY, not X inverted Y. There, that's how it should be. Now let's turn to arithmetic, performing binary arithmetic. So this is an example arithmetic computation, an addition of these two numbers. And when you perform this addition, this is how it evolves. So these two will yield a 1, no carry. These two will yield a 0 and a carry. Then this one with these two will yield a 0 and a carry. Then these three will yield a 1 and a carry. Then these will yield a 1, and then these ones over here, that's your result, the sum. Now, to perform binary addition, for each column, we look at the 2 bits to add, which is the corresponding bit for the operand A, and the corresponding bit for the operand B, and possibly a carry from the previous column. With these 3 inputs, we look to produce 2 outputs. One will be the sum that goes in down here in this row, and the possible carry. What is the logic for producing this sum on each column, or stage as we call them, and the next carry to be carried over to the next column or stage? This is the truth table of how we want these bits to be generated. This table shows all the possible combinations for the values of the bits A, B, and the possible carry that comes from the previous stage. For each particular combination, we write down what the corresponding sum bit will be and what the next carry will be. So looking at this, we have all zeros, so the sum will be 0 and the carry will be 0. Looking at this entry over here, 1 and 1 will yield a sum of 0 and a carry for the next stage. Looking at the last row, 3 ones will yield a sum of 1 and a carry for the next stage. So this is how we want these bits to behave, and any circuitry that will be producing these has to behave like this. So basically, we started with a truth table for the hypothetical Boolean functions that would potentially be able to compute these bits for us. Next, we look at the entries of the truth table that the corresponding output is 1. So when we're looking at the generation of this value, we're looking at its corresponding column and we mark the positions of the ones. What we want is to get an expression that will basically tell us when this value should be 1. We do not care about the places where this value is 0, because if it's not 1, it's going to be 0. Therefore, all we care is to specify at which combinations, at which input combinations, this bit will be true, will be 1. So from here, we see that the input combinations which yield 1s for this bit will be these ones. So what we do is we take the OR, the logical OR of all these terms, all these logical terms, and we make this expression. This expression shows how this should be computed via a Boolean logic expression. Next, we look at the column for the carry. We do these separately from each other because they are computed separately. They're produced independently. Therefore, we're looking at this column and mark again the positions for which this bit will be 1. And we see that this bit is a 1 at these input combinations. And then we sum up all of these combinations. We take the logical OR and we come up with this expression. Let's take a look at these expressions, this one and the previous one. So on this expression, what we have is a form that shows that the SI is true when either this is true or when this combination appears, or when this is true, that is when this combination appears, or when this is true, i.e. this combination appears, or when this is true, which means that this combination appears. So that is what this says. It says that this bit will be 1, logic 1, true, when either of these combinations appear, which are these. And that is how, from the truth table, we can generate an expression that actually describes the function that the truth table describes. So similarly, for the carry, we have a similar situation where again we have marked the positions where it is 1, and then we collect all the terms that correspond to the combinations that make the carry 1. And then we say that the carry is going to be the logical OR, the sum, in other words, of these terms, which means that the carry is true, is logic 1, when this appears, this combination appears, or this combination appears, right here, or this one right here, or this one right here. Now, we can take the expression that we came up with and we can perform some Boolean manipulations to reduce it to a simpler form. You will see that this expression is actually the same as this expression. All of these manipulations leave the truth value of this expression unchanged. So this one is equivalent to this one, and this one is the same as that. It really computes the same carry, but in a simpler way. Let's go over this since we have it here and practice our manipulating skills, algebraic manipulating skills over here. So this expression can be transformed to this expression. I have turned this one into red. I've left the rest of them unchanged. And then I have duplicated this another 2 times. So basically, this term has been replicated 3 times, which doesn't change anything. This is like x plus x plus x, which x plus x is x, so x plus x plus x is just x. So this hasn't changed anything. It hasn't changed this Boolean expression. But it allows us to then take these terms and pair them with each one of these terms. So these parentheses show how this term is paired with this one, and this term is paired with this one, and this term is paired with this one. So nothing has changed over here either. We have just grouped the pairs together, but otherwise, really, nothing has changed. But now, from its group, we see that there is a sub-expression that can be factored out according to the distributive law of Boolean algebra. So you can factor out the BC term from here and leave the A and A complement in the group, in the parenthesis over here. So you can see it going the reverse, that if you were to apply the distributive law, this will be then distributed to each one of these and will produce this one back. But anyhow, we go this way because then these 2 terms actually can be cancelled out, because A and A complement, A or A complement I should say, is 1. According to the Boolean logic rules, A or the complement of A is 1. So this would be a logic 1, and the logic 1 logically ended together with anything, just leaves that anything unchanged. So this reduces to just this. Similarly, we can factor out a few other terms here and leave similar situations, which also amount to logic 1s. And then, of course, logic 1s ended with something else, leave just that something else. So this is the expression that is equivalent to this one, but it is in reduced form. Now, what we do is, based on this expression, we can actually build a circuit that will implement this function in a physical implementation, in a circuit implementation. So the way we do it is we use Nand Gates to implement each one of these terms. So you see that this gate here implements the term A and B. This gate here implements the term A and C, this one. And the last one implements the term B and C. And then all of these are ORed together to produce the actual carry bit. So, bottom line, what have we accomplished here? We went from a truth table specification of how the carry should be generated, or how the circuit implementation that we're seeking should behave, and then from the truth table we obtained a Boolean function that describes how that function should behave. Then we manipulated this expression to minimize it and get an equivalent expression that is much simpler and therefore can yield a circuit that is as simple as possible. And from the expression, we just followed what the expression says. We used AND gates to build the AND terms and an OR gate to collect all of the outputs of the AND gates into a sum, and that is it. So this happens to be a sum of products implementation, and so it ends up in a standard circuit that consists of AND gates, a whole bunch of AND gates, and they're collected by the OR gate and summed out. Similarly, for the sum bit, this was the expression that we got out of the truth table. And we can manipulate this algebraically again and get this expression. So algebraic manipulation shows that we can get this expression as equivalent to this one. Now you can also verify this by taking the truth table of this expression and the truth table of this expression and see that they are in fact the same. Now this implementation here results in this circuit representation, or circuit implementation, I should say. Again, all the terms that appear over here are implemented one by one. So this gate over here takes as inputs the input B and the inverted input A. So it actually implements this term right here. This gate takes A and the inverted B, so it implements this term over here. The sum is implemented by this OR gate. And then this is ANDed together. Okay, this is ANDed together, this AND gate, with the inversion of the C signal. And that implements this whole term. Then this term here is implemented over here. You see, the output of this gate is this, and this appears over here, except that the whole thing is inverted. So this output inverted basically produces this part. And then an AND gate ANDs the signal C together with the output of this over here. See, the signal C is ANDed together with the output of the inversion. And then the two terms, this one and this one, they're ORed together because of this. They're ORed together through this gate to produce the output. So there you go. We have an actual circuit implementation for producing the sum bit on every stage of the addition. Putting those two things together yields this, which is the two circuits that we had put together, wired together. So this produces the sum, this produces the carry. They operate on the same inputs A, B, and C. So this circuit here is called the single stage adder because it will be a simple circuit that will implement the addition at a single stage or column of the computation that we saw earlier, which was this one. So at each column, at each stage, that is the operation that we have to perform. Now imagine that you use replications of that circuit on each one of these states in order to produce the sum and the carry at each stage. Then what you have is this. See, this is the single stage adder. As a matter of fact, this does have a name because of how particular it is. In logic design, it's called a full adder. And what it is basically the single stage adder, and then you can replicate it like this. Now, the very first carry should be 0 because there is no carry, there's no previous stage. As a matter of fact, you could use another circuit that would be only consisting of the sum part, but not the carry circuit. That would be called the half adder. I'm just referring to it because these names are common and you may bump on them, and that's why I'm referring to them. Otherwise, they don't really make that much of a difference at this stage. The important thing to understand is that by cascading or replicating this basic block, you can make a circuit that will add any length of binary operands. So you will feed the A operand bits at these positions. You will feed the bits of the operand B at these positions, and then here you're going to get your sum. In fact, these circuits are manufactured and are sold in chips that are called arithmetic logic units. They don't just do addition, they do a lot more than that. But here's an example of such a chip. This is the 74181 chip. And if you followed this link, then you would get the data sheet for the particular chip. And this is an excerpt of that data sheet that shows what the data sheet looks like. So it shows you the way the chip looks. So this is going to be the little chip, and these are going to be the pins of the chip. And over here, these signals designate what each pin is for. So there are the pins A0, A1, A2, A3, and B0, B1, B2, B3. And then there are also the output signals. And also there are control signals that are signals that control the function of the chip. By providing different combinations of values to the signals, you control what function this chip is going to perform on the operands A and B, with the result to appear on the outputs. And of course, there are some other signals that are used for either cascading chips like these to make longer circuits or other matters which are outside the scope of what we're trying to do over here. Now, going a little further into the data sheet, you will find a table that shows how the chip operates. So this table shows that depending on the signals S0 to S3, I'm sorry, the signals S0 to S3 are in fact the control signals. The output signals are the F0 through F3. Three of them appear over here and another one is over here. So these show the logic state for each signal. L stands for low, H stands for high. So low basically means logic 0 and high means logic 1. Or low means 0 volts and high means 5 volts. So depending on what the input combination of the control signals are, this table shows what kind of function will be performed. So if you look at the last line, when all of these signals are high, then the function to be performed is that the output is going to be A plus 1. If the combination is this one, then the output is going to be A plus B plus 1. Now that also depends on these other signals that also are used to refine the operation that the chip is called to perform. So enough of this, just wanted to show you what a ALU that is actually on the market looks like, and what the datasheet looks like, and how they behave. Inside the datasheet, you can also see how the chip is made. So this over here is actually the schematic of the logic circuit that implements the functionality of this chip. So this is how this is made, with all these gates. We do not need to go over this, but just wanted to show you that using these basic logic gates, we can now make circuitry that does a lot more complicated functionality. All the digital systems that we have shown so far are called combinational systems. All the signal paths flow from the inputs to the outputs with no signal feedback. So if you consider this circuit here, these are the inputs, this is the output. The signal flow is from inputs towards output with nothing turned back to flow back as input again. The electrical effects of a new input never mixes with any residual effect of previous inputs. So if you provide new inputs for A, B, and C over here, the output that you will get will depend only on these inputs, and it will be totally independent of what inputs you provided before. The electrical signals flow strictly forward from inputs to output, hence output always depends on the current values of the inputs, and past inputs do not matter at all. There is no memory effect. But this is not always the case. There are situations where we do want memory in the system. For example, consider a vending machine where you go and put coins in, and you're putting them in sequentially. The system at any given time sees what coin you're inserting, but it also remembers what is the previous sum. This is a very good example to contrast from this one. In this case, the output depends only on the current inputs and not on the history of inputs. But in the case of the vending machine, where you sequentially insert the amount that you need to pay in order to buy your chocolate, there it is important that the system does remember something about the past input. It is important to have a residual memory that reflects at least the sum of what was provided as inputs. Hence, the need for sequential digital systems. Consider here this circuit which has feedback. You see that you have two inputs, R and S, but this output is actually fed back into this gate. In this case, you can see that this value actually affects the future generation of output values at this line, because it transiently affects itself. Take a look at this red path. Starts from here, and this value is transmitted back here, so it affects this output, which affects this output, and this signal is carried back here, so it affects this output, and that affects the generation of the new value for Q. So what happens here is that Q affects itself. Q takes place in the generation of its own value. And because of that, past inputs have a residual effect that remains for some time in the future. So the Q will depend on the values of R and S, but also on the previous value that it had, which previous value depends on the previous values of R and S. So what circulates in this loop, in this red loop, is basically a residual effect that cumulatively represents something of the past of these inputs. Therefore, this circuit actually has memory. This circuit is actually known as the RS flip-flop and serves as a 1-bit memory. The reason that this system exhibits memory is exactly because of the fact that there is feedback in the circuit. And such systems are called sequential because the output depends on the current inputs, but also on the sequences of inputs of the recent past. The RS is known as a flip-flop. There are other circuits like the RS flip-flop, which are also called flip-flops, just of different types, which are basically variants of the RS flip-flop with better properties. The most widely used ones are the JK flip-flop and the D or delay flip-flop, and they come in versions that are either asynchronous or synchronous to a specific additional clock input. The JK flip-flop improves on the RS flip-flop, which has a problem, and that is that it can fall into an unpredictable state if both inputs are activated at precisely the same time. So the previous RS flip-flop is augmented by putting these gates here and these feedbacks with the additional inputs that are shown over here. This flip-flop is also a basic 1-bit memory block, and it does not have the drawbacks of the RS flip-flop. This one here is another modification, which is this flip-flop where the two inputs are not independent and there simply is one input which is fed directly to one of the inputs here and then in an inverted fashion is fed to the other one. This is called the delay flip-flop, and the delay flip-flop simply locks and holds onto the input which is present at the input D at the time that the input E is triggered. So whenever this is triggered, whatever appears over here will pass into the circuitry because these gates will open and will allow their other inputs to pass to their outputs, and then that input is going to be latched into this RS flip-flop, and this flip-flop will keep them steady. It will latch onto them and keep them steady at the output as long as the signal E is not activated. When the signal E is activated, then a new input will be read and be latched on to it. Now, we do not need any more detail on sequential systems for our purposes here because it doesn't really add anything of essence for what we need to do in the computer architecture course. But if you're interested in logic design, then there are classes in logic design that you can take as well. Now, using the flip-flops, we would like to talk about registers. Using the flip-flops as building blocks, we can construct circuits that can latch and hold entire strings of binary data. So you use arrays of flip-flops to hold arrays of binary data, i.e. strings of binary data. So these circuits are called registers, and this here is one such example. This is the chip 54165, and as you see, it consists of a bunch of RS flip-flops cascaded together. They're connected in a chain with some other logic controlling signals, and it is able to take 8 inputs and latch onto these 8 inputs in the flip-flops that it includes, and that happens under the control of an input that is called clock, a synchronizing input that allows the register to latch onto whatever input appears over here at specified times that are in sync with a control signal called clock. It is also able to input a binary vector serially in. You see, you can put inputs here that will be latched onto this flip-flop, and then next the output of this flip-flop can pass onto this one, and the new input can shift onto this one, and then you can shift serially a bunch of inputs from here into this structure. As another example, this is the 54195 chip that shows 4 flip-flops which can latch onto 4 external inputs, A through D. Okay, A through D. So again, you have flip-flops here that will latch onto the inputs A through D, based again on some controls that you have over here. The features of the 54195 are that it can take parallel inputs, it has parallel outputs, so inputs that are latched on will be available and held steady at these outputs until the next load, and it is actually possible to do shifting as well. In other words, shift the contents of the register up or down, or left or right, depending on how you view this schematic. And remember, this is important because shifting left or right of a binary vector corresponds to multiplying the vector by 2 or dividing it by 2. Counters, another very useful circuit that is also available as individual chips. This is an example of a counting circuit. You have 2 delay flip-flops that are connected in cascade, and you have an input that is designated over here as clock. So input pulses arrive over here, and this is showing over here in a timeline inputs arriving at the clock input, and the signals A and B, the binary values of A and B at all time indicate how many pulses have arrived. So in the beginning, you start with these being at zeros. After a clock pulse, then A is going to be 1 and B is going to be 0. After 2 pulses, B is going to be 1, A is going to be 0. After 3 pulses, both are going to be 1s. Now, given that this is a 2-bit counter, it can only count 2 to the power of 2 different entities. Therefore, it can only recognize 4 different states. So it can count only up to 4, with 4 not included. It will count modulo 4. So after a bunch of pulses, the circuit is going to reset and start over again. But it is a basic counter. Of course, you can put more flip-flops over here so that you are able to actually counter longer sequences. We're going to see later that these counters are essential as sequencers to provide sequencing control signals that is inside a computer. Now, looking at the inside of a computer, taking a first global view of the parts that make a computer, we will see that a computer consists of a bunch of registers that hold data. It consists of an arithmetic logic unit that performs operations on data operands, and it has a control unit, a very important control unit. This control unit will provide codes to the arithmetic logic unit so that the arithmetic logic unit will perform the appropriate operations. Recall from this data sheet of the arithmetic logic unit that we were examining here that it can perform a whole bunch of functions, but it has some control signals, and inputs fed at those control signals determine what function is going to be performed. That is the purpose of the control unit. Based on instructions of a program that resides in main memory, the control unit instructs the arithmetic logic unit about what operation it needs to perform in order to carry out the program instruction. The control unit also will provide the signals to establish and activate the data paths that will connect the appropriate registers to the arithmetic logic unit as operands. Recall our discussion of this case where input signals were connected to these output signals in any desirable way based on what control signals were provided right here. So similarly, this control unit can provide the control signals that will establish the data paths that will feed the appropriate registers at the inputs of the arithmetic logic unit, and will also provide the control to the arithmetic logic unit for what operation it needs to perform. And that is the bird's eye view of what a computer consists of and how it's made. The control signals must be generated in a proper sequence. That is the important thing to understand and is what really makes things a little bit more complicated. For example, when you are going to perform an operation over here, first you must make sure that the data paths have been established for the operands to be provided to the arithmetic logic unit. Then you provide the control code to the arithmetic logic unit so that it will actually perform the function that it's supposed to on those operands. And then you have to specify where does the result go, to which register the result will be directed. As you see, these tasks have to happen in a particular sequence. First, you have to provide the operands, then perform the operation, then direct the output to the appropriate register. So all of the control signals that will perform or will coordinate the hardware to perform these operations have to appear in a specific sequence and timing, of course. So that concludes this section where we discussed Boolean algebra and generation of digital logic circuits that will perform specific functions which have been described either in terms of truth tables or Boolean expressions. So what is next? In the following sections, we will go into more detail about how the hardware operates and how it is coordinated in order to perform the computing tasks. We will look into the way data is handled and the way instructions are executed by the hardware. And then we will discuss various options in architecting the hardware at higher levels and the way these architectures achieve high performance. And that is the end of this section. Thank you very much for staying with me.